In this video, I'm going to walk through slides I've made on the LoRA Learns Less and Forgets Less research paper by Dan Biderman et al. And I found this to be a really interesting paper that compares full fine-tuning performance with LoRA in two challenging domains of code and math. So here's my outline. I'm going to start with main takeaways, and then I'm going to introduce the two research questions they ask in the paper. I'm going to talk about the data regimes that they explore, how they evaluate their performance. I'm going to talk about the low rank hypotheses that are presented in background work and how this paper shows a counterexample to that hypothesis. I'm going to go into a little bit of depth into LoRA and do a background of those concepts. Then I'm going to go into the results of the LoRA Learns Less and Forgets paper, and I'm going to end with the LoRA recommendations that they present. I had 6 main takeaways from this paper. LoRA underperforms full fine-tuning when rank is low, and even for high rank for continued pre-training. LoRA maintains source domain performance better than full fine-tuning. LoRA mitigates forgetting more than dropout or weight decay. LoRA maintains diverse generations similar to the base model. And full fine-tuning learns perturbations with rank 10 to 100 times LoRA rank. And finally, LoRA is sensitive to hyperparameters. So I found that these two quotes kind of motivated their two research questions. The first one from the paper is that the jury is still out on whether LoRA compromises performance compared to full fine-tuning. And secondly, by training fewer parameters, LoRA constrains the fine-tuned model from diverging significantly from the base model. And this translates into their two research questions. First, which is under which conditions does LoRA approximate full fine-tuning accuracy on challenging target domains, such as code and math? And two, when performing continual learning on a new domain, to what extent does LoRA mitigate forgetting of base model capabilities? The two target domains that they pick are code and math. Here's the data that they use for training. CPT means continued pre-training, and IFT means instruction fine-tuning. And there are two domains of code and math. For CPT code, they use the StarCoder Python dataset, and they use 20 billion tokens. And this is the Python subset of StarCoder, and then they've subsampled that down to 20 billion tokens. The Python subset itself is 64 gigabytes. I'm not sure what the 20 billion token subsampled size is. For CPT Math, they use the Open Web Math dataset, which is 14.7 billion unique tokens, and they repeat that to get up to 20 billion tokens. And this is about 27 gigabytes. For instruction fine-tuning code, they use the Magicoder Eval Instruct 110K dataset, which is question-answer pairs and about 250 megabytes in size. And for math instruction fine-tuning, they use MetaMath QA, which is about 400 question-answer pairs and is about 400 megabytes. For evaluating their target domains of code and math, for code, they use human eval, and they use the pass-at-one metric with 50 generations, which we'll look into a little more detail next, or in a bit. And this data set has 164 items, where each item is a description, a docstring, and a function signature, and based on that, the model is expected to write a program. And for the math domain, they have the test set of GSM 8K, which is grade level math school word problems. They use the pass-at-one metric, and there are about 1,300 items in this data set. So here is the human eval pass-at-k metric that they use for evaluation. The variable n is the number of generations, which is 50. C is the number of correct generations, which I didn't see explicitly defined based on what I understood from the paper. And then K is the size of sample set considered for acceptance. So in this numerator here, you have 50 minus C total generations, and then you're choosing 1 out of that. So you have 50 minus C generations to consider. To evaluate the source domain, so in other words, to see, how much does the model forget what the base model understood, they have 3 domains of language understanding, world knowledge, and common sense reasoning. And they have three data sets: the HeliSwag data set which has 70,000 items, the Wino Grande data set which has 44,000 items, and the ARC Challenge dataset, which has 7,787 items, not to be confused with the ARC AGI, ARC Prize dataset. This is different. Here's a screenshot of HeliSwag, where you're given a event, and then the model is asked to select the best ending or best continuation to that given context. Here's an example of the Wino Grande dataset where you're given twin sentences and you have to pick the correct pronoun that is being referred to by the given word. And then the ARC dataset is a grade school level multiple choice science questions. So next we move on to this low rank hypothesis, and this is from the original LoRA paper, where they say that we hypothesize the updates to the weights also have a low, quote, intrinsic rank during adaptation. From the paper Measuring the Intrinsic Dimension of Objective Landscapes, they show for two different models. They have a fully connected network with about 200,000 parameters, and they have a convolutional network with about 45,000 parameters. And in each case, they show that a very small number of dimensions, so about 800 dimensions here, and about 300 dimensions here, is needed to capture 90% of the full parameter accuracy. So this is pretty strong evidence that for MNIST, for these types of models of these sizes, you can have a few hundred parameters to capture the full parameter accuracy. And then from the Intrinsic Dimensionality Explains the Effectiveness of Language Model Fine-Tuning paper, they show that by optimizing only 200 trainable parameters randomly projected back into the full space, we can tune a Roberta model to achieve 90% of the full parameter performance levels on MRPC, which is a sentence similarity classification dataset. So you have these examples that basically say that we only need to tune a low-rank subset of our full parameter matrices. And the counterexample that they show in the LoRA Learns Less and Forgets Less paper is that singular value decomposition shows that the difference between fully fine-tuned and base model weight matrices is high rank. So you need a significantly higher number of rows and columns, dimensions, than LoRA to explain the difference between fully fine-tuned and base model weight matrices. And this goes against the LoRA and other hypotheses that fine-tuning results in low rank perturbations. And we'll look at this in more detail in this slide. So in their counterexample, they show on the left, they show that full fine-tuning barely changes the spectrum of the base model's weight matrices. So these are the singular values at the different indexes. The orange line is the fine-tuned model, and the dotted line that's just beneath it is the base model, and the green line is the difference between the two, which very quickly gets under value of 1. So the difference between the singular values between the fine-tune and base model is very small. So that's that first part. And yet the difference between the two, so the perturbation, is high rank. So on this chart here, we can see that it takes about 15, 16, 1700 singular values to explain 90% of the variance in the difference between the two weight matrices, the base and the fine-tune. So 1500, 1600, that dimension is much larger than the rank that we see when we are training with LoRA, which is anywhere from 2 to 64 or 256 or 512 dimensions. So that's something to keep in mind as we kind of move forward. Now I'm going to switch to showing some background on LoRA itself. Here's a screenshot from the LoRA paper, which shows that you have two matrices, A and B, where they both share a very small dimension relative to the pre-trained weights. That's R, that's our rank, kind of the key hyperparameter for LoRA. And we are training those parameters only during fine-tuning. And the result is that we have, a much smaller number of parameters to train. So, it's not unreasonable that we would have only 1% of our pre-trained weights that are actually being trained because we have such a small rank that we are using for these matrices. On the left side, here are some equations of interest, or some expressions and equations of interest. The fine-tuned weight matrix is equal to the pre-trained weight matrix plus some delta. And for LoRA, this delta is a hyperparameter gamma times your A matrix times your B matrix. And these A and B matrices are LoRA adapters. The A matrix is some dimension D that comes from the pre-trained weights by R, which is your rank, LoRA rank hyperparameter. And then your B matrix goes from that rank R back up to K, which is, whatever your other dimension of your pre-trained weight matrix is. So in this example here, our pre-trained weight matrix is D by D. And then our gamma R is equal to the alpha hyperparameter divided by the rank R hyperparameter. And this is a scaling factor that gets multiplied by the matrix multiplication of our two adapters. The initial values of A and B, so A is a normally distributed values, and B is just 0. And the highlight here about B being 0 is that when B is 0, this product is 0 as well. So our delta, our difference, is 0. And so we're starting out our LoRA training with our pre-trained weights. So that is the reason we have one of these set to 0, so that we start our fine-tuning with our original pre-trained weights. And as we're looking at LoRA training, there's 3 things that we consider for memory. I mean, there are other things as well, but 3 main things. We look at the weights that are being stored. So we have our weights of matrix A, which is D by R, plus R by K, which is matrix B, or adapter B. And then we also have to store our pre-trained matrix, D by K. And so pre-trained matrix is going to be used in the forward pass during training. So we do have to store the pre-trained weights. The gradients, however, are only going to be for our adapters. So we have D by R plus R by K parameters that we have to store for gradients. And then if we're using the atom optimizer, which has momentum and variance stored, we have to have 2 times D by R, which is, momentum and variance for matrix LoRa adapter A, plus momentum and variance for LoRa adapter B, which is, 2 times R by K. So these are some kind of just rough numbers to keep in mind, and we'll look in a little more detail. This was this really well written piece in the appendix of the LoRa Learns Less and Forgets paper, and I'll just read off that most memory requirements relate to model states and then residual states. So most memory requirements are model states, which include the parameter weights, the gradients, and higher order optimization quantities such as optimizer momentum and variance in the atom optimizer and the momentum in the Lion optimizer. So that's what we were just looking at for LoRa. We were looking at weights, gradients, and optimizer states. And then the remaining memory requirements come from residual states, which are activations and temporary buffers for intermediate quantities in the forward and backward pass. And these will require more memory when increasing the batch size and maximum sequence lengths. So when you're storing single precision, you have a master copy of the tuned parameter weights, you have the gradient, and then you have all of the optimizer states. And the key thing here is that LoRa offers memory savings with respect to the model states. So you still have your activations and temporary buffers for intermediate calculations because we're still doing a forward pass using the pre-trained weights during training. So the residual states don't have LoRa savings, but the model states do. They break down some heuristics of how to calculate rough memory estimates. So storing the master weights in FP32 requires 4 bytes per parameter, while storing the gradient requires 4 bytes per tuned parameter. And then for atom, we have 4 bytes for the momentum term and 4 bytes for the variance term. So if we have a 7 billion parameter model, which is the model being used in this paper, the Llama 2 7 billion, you have 4 bytes times 7 billion parameters for the master weights. You have 4 bytes times 7 billion for the gradient, and then you have 8 bytes times 7 billion for atom. And so this is our fully fine-tuned memory requirement estimate, which is about 100 gigabytes. And then the Lion optimizer is going to use 4 fewer bytes for your optimizer state because it only stores, I think, momentum. I don't think it stores the variance. So that's going to take about 80 gigabytes. And then if we look at LoRa down here, so instead of 100 gigabytes, if we have everything in FP32, it's going to be about 30 gigabytes of memory. If we store the pre-trained weights in bfloat 16, this brings it down to about 15 gigabytes. So here are just some examples they have, which I thought was really useful just to kind of start building some intuition on how much memory these things take. All right, so that's the background, and that kind of sets the stage for what we're doing. All of their results are calculated for Llama 2 7 billion. In an earlier preprint, they also had some Llama 2 13 billion results, but I found that in the official kind of printed copy that's also updated on archive, they only do things with Llama 2 7 billion. All right, so the main results. When we're looking at Code CPT, Code IFT, Math CPT, and Math IFT, and we're looking at full fine-tune results compared with LoRa. In 3 of these domain/regimes, full fine-tune outperforms LoRa. But I think it's really important to note that for Code IFT, LoRa actually beats out full fine-tuning by a 1,000th of a point. And then for Math IFT, LoRa is still, quite competitive. So, one of the main takeaways they had is that, for instruction fine-tuning, you should use LoRa. But for continued pre-training, LoRa performs relatively significantly worse. And in the parentheses are just some details about how many tokens they trained it for continued pre-training, or how many epochs they trained for instruction fine-tuning, and what the rank was. I think that's everything I wanted to share on this slide. I think the one more thing is that when we look at LoRa for math continued pre-training, and we look at let's I think that's it for this one. There's something on the next slide I want to share. So the main takeaway here is that LoRa learns less, and I think kind of a secondary takeaway is that LoRa does really well on Code IFT and decent on Math IFT. So then we look at source domain. So do these models remember things that the base model was good at? And again, we have the same domain regimes of Code, CPT, IFT, and Math, CPT, and IFT. The evaluation is done on these 3 source domain benchmarks. We basically take the average of the accuracy, and then we have these values here. And in every case, LoRa performs better, and significantly better in some of these situations. So we'll see here that I've highlighted that this is an R rank of 16. This is an R of 256, this is of 16, and this is of 16. So my understanding is that when you're tuning fewer parameters, which is what you're doing when you have a lower rank, you're changing less of the base model, so it's going to remember more of the source domain. So that was my understanding of why R equals 16 does better than R equals 256 for some of these benchmarks. But in each case, LoRa beats full fine-tuning. So the main thing is that LoRa forgets less. We're looking at the same data here, but we're looking at it in these charts. So the first column is continued pre-training. Second column is instruction fine-tuning. The first row is for code. That's evaluated on accuracy in human eval. Second row is math, which is accuracy in GSM 8K. And in each of these charts, when we move up the y-axis, we're talking about the model learning more in the target domain. When we move to the right, on the x-axis, we are talking about the model forgetting less in the source domain. So how much does it maintain of that base model capability? And then when we move to the top left, from the bottom right to top left, we're talking about training longer. So if you noticed here, the marks are larger here than they are here. So for continued pre-training, these are larger billions of tokens that are being trained. So this is 0.25, and this one up here is 20 billion. For instruction fine-tuning, we go from, I think it's like 2 epochs up to, I think, 16. And I think the interesting thing to highlight, and I think it really shows up in this instruction fine-tuning code example, is we have this Pareto distribution for LoRa, where here you see a very significant improvement in accuracy in our target domain with almost no loss in source domain capabilities or base model capabilities. So, LoRa in general, yes, it does learn less, but not only does it forget less, the cost of learning more is not as high as it is for full fine-tuning. That being said, some of these other charts are fuzzier in terms of what we can interpret. Look at math IFT, it's telling a different story. When we look at continued pre-training math, it's difficult to tell because it just doesn't do really well on the target domain in general, but you can sort of see a little bit of that Pareto distribution. So just another way to look at this information. They also provide a whole series of tables in the appendix, which shows, for each set of training length, what are the different ranks for LoRa, what is the full fine-tuning accuracy, and they lay all that out. And this is what one of those looks like. So this is the continued pre-training on code. And in general, the pattern I saw was that when you're looking at target domains, so human eval or GSM8K, in general, rank 256 does better than 64, which does better than 16. So, you have more parameters, you're going to learn more, is what I took away from it. And then generally, as you train longer, you're going to also improve what you learn, the amount that you learn, and the performance on the target domain evaluation set. Okay, so that's one set of results, and kind of the main set of results. A secondary objective they had was to see how does LoRa compare with regularization, which is dropout and weight decay. And the chart on the left shows the accuracy on human eval, and then the number of epochs that we're training, and then it shows a host of different models. So we have base model, we have weight decay of 001, we have weight decay of 5e neg 5. We have two different attention dropout values, and then we have fully fine-tuned, and then we have two different LoRa's. And then on the right, we have our source domain accuracy on the y-axis, and x-axis is the amount of training that's done. And the main takeaway, two main takeaways, is that when it comes to learning, LoRa in general does better than dropout and weight decay, although attention dropout of 0.05 is actually performing better, but the other three are not. And then when it comes to forgetting, we can, considerably see the benefit of using LoRa because it forgets significantly less than all of our weight decay and dropout values, as well as full fine-tuning. So LoRa is a better regularizer than a dropout and weight decay because it learns more and it forgets less. Then they looked at sample diversity, so generation diversity based on different samples. So this is for human eval. And in terms of diversity, what does it mean to have a unique response? They're looking for exact string matches. And let's kind of take a minute to look at the layout of this chart. So the first column is the base model. The second column is the fully fine-tuned model. And the third column of charts is our LoRa model. The first row in orange are the incorrect generations. So these are generations that failed our test for human eval. And then the second row in green are our correct generations. And these are they passed our human eval problems. There's 164 problems, 50 generations each. So we're looking at about 8,000 generations in total for each case. So things that jump off the page for me, number one is that the base model's incorrect generations are the most diverse. And number two is that the base model's correct generations are less diverse than the incorrect ones, but much more diverse than the fully fine-tuned, right? So fully fine-tuned, there's a couple of unique generations that happen, 50 times, and then a couple other ones that happen 20 times, and so on and so forth. And we see a similar trend here, right? So there's 30 generations for a couple of these, or 30 counts of a couple generations, 20 counts of other ones, and so on and so forth. And then the third thing, and I think the main takeaway for LoRa, is that LoRa falls somewhere in between the base model and fully fine-tuned model performance. So the LoRa generations for incorrect responses are not as diverse as the base model, but they are more diverse than the full model, right? So they're less skewed, more uniform. And same thing for correct generations, right? So the correct generations for LoRa are not as diverse as our base model, but they are more diverse than the full model. And the caveat that they provided is that exact string matches are not the only way to look at similarity. You could of course look at, semantic similarity, and that might tell a different story or a more nuanced story. But the general thing here is that LoRa maintains generation diversity more than full fine-tuning. All right, so the next thing we're going to look at in terms of their results is this counterexample to this low rank hypothesis. And to do that, I just want to reiterate this equation here. So our fully fine-tuned weights is equal to the pre-trained weights plus some delta matrix. And this delta matrix, if we just rearrange these items, is the difference between the fully fine-tuned and pre-trained weight matrices. And this delta is what they perform singular value decomposition on, and that's what we're going to look at next. So these charts show the rank required to explain 90% of the variance in that delta matrix, in that difference matrix. And another way I think of that is these charts, the rank you need to explain 90% of the difference between your pre-trained weight matrix and your fully fine-tuned weight matrix. And in each case, we can see that we're dealing with, thousands of dimensions. So here it's about, in general, for these attention modules, Q, K, V, and O, we're dealing with around 14, 15, 1600 dimensions. That's our rank. Again, much, much higher than LoRa, which is 2, 4, 16, 64, 256, maybe 512. And then for these MLP modules, the down and up layers, we can see that they have a higher rank, around 2600, 2800. So the main takeaway here is that the effective rank that explains the difference between fully fine-tuned and pre-trained model weight matrices is 10 to 100 times larger than the LoRa rank. And so this I see as a counterexample. I mean, I don't see it, it's explained in the paper, but this is a counterexample that fine-tuning results in low rank perturbations, right? We're seeing that this is a very high rank or relatively high rank perturbations that are a result of fine-tuning. One thing I'll just add as a note is that as we go up on these charts, we're looking at longer and longer training. So the bottom is 4 billion tokens, and the top is 20 billion tokens. And again, this is for continued pre-training, so we're only looking at CPT. They did not do the analysis for instruction fine-tuning. Just to recap the low rank hypotheses, the hypothesis was that there's a low intrinsic rank, and this is a counterexample to that. For MNIST on these networks, we could see that 90% of the full parameter performance is captured by low rank, and that was evidence to show that low rank is all you need. And then we also saw that only 200 parameters are needed to achieve 90% of the full parameter performance for Roberta on these sentence similarity tasks. And again, here we are showing this high rank weight updates are needed to explain the difference between full fine-tuning and base model weight matrices when we're talking about continued pre-training. And one caveat, and I think it's an important one, is that the observation that full fine-tuning tends to find high-rank solutions does not rule out the possibility of low-rank solutions. Rather, it shows that they are not typically found. An alternative interpretation is that the rank needed to reconstruct the weight matrix is higher than the rank needed for a downstream task. We only present for continued pre-training setting. It's possible that instruction fine-tuning would reveal different results. So, it's not disproving the hypothesis and solidly or confidently, but it's an interesting and I think a really interesting counterexample. Another result is that LoRa is sensitive to hyperparameters, and this is something they mentioned as, I think it was a helpful kind of warning of, hey, if you're going to use LoRa, make sure you try different things, right? So that's kind of my takeaway from this. So we have a rank of 16, a rank of 64, a rank of 256. This is the code instruction fine-tuning data set, and this is our human eval pass at 1 metric. And in each case, the yellow line, which is just targeting the attention modules, is the worst performing LoRa. And when you target the MLP modules, or when you target all modules, both MLP and attention, you get superior training results. So the takeaway here is that we should target MLP or all modules, not just the attention modules for LoRa, and we will get better results regardless of rank. Another hyperparameter nuance is that LoRa generally requires 1 order of magnitude higher learning rate than full fine-tuning. So here they again train this on the code IFT dataset for 2 epochs. They calculate the accuracy on human eval for each of these learning rates. And black is full fine-tuning, purple is LoRa. And in this case, we see that the best LoRa performance is about 10 to the 3, -3, and the best full fine-tuning performance is on the order of 10 to the -4. And we see that on the MetaMath QA, which is the math IFT evaluated on GSM 8K, we see a similar result. We see about 1 order of magnitude higher requirement for LoRa. Another result is that LoRa requires less peak memory, but it also trains slower. So the training slower sweep is done here. So they sweep through different batch sizes, and then they calculate the tokens per second. And the green is full fine-tuning, which is like 30% or so more than the throughput. So this is something that's interesting, that there's more kind of overhead that slows down training. And on the other hand, you can use much less GPU requirements for LoRa than full fine-tuning. So, for a batch size of 8, we need only about 10 gigabytes for LoRa and about 18, 20 for full fine-tune. Of course, that depends a little bit on the rank. But as batch size increases, the size of intermediate activations increases proportionally. So that ends up dominating the required memory. So that's why we see this increase in required memory, peak active memory, when the batch size increases for LoRa, as well as for full fine-tuning. And they also look at different optimizers. So they try the Lion W optimizer, and they find that it performs better than the Atom W optimizer. And I'm not going to go into detail. I'm not as familiar with Lion W, and I'm not going to compare kind of the details of it. But I just wanted to highlight this in terms of, something else to consider, when we're training things with LoRa, that, okay, we need to try different optimizers because there may be a significant improvement. So the dotted line is Atom, the solid line is Lion, and we can see that the peak LoRa performance is, there's maybe like a 5%, 5-point difference between the two. They also find that the alpha LoRa parameter is sensitive, and you have to set it to a particular value, and the value that they found was twice the rank. So here, this is on code IFT, whereas this one here is on I think this is continued pre-training. So this is math CPT, and here in each case the rank is 256, but the alpha value goes from 32 in this kind of dirty yellow, kind of beige color, to 256 in red, to 512 in blue. And they find that for this particular learning rate, we get the best target domain evaluation accuracy when alpha is 2 times R. So the optimal choice is alpha equals 2 times R. So that's one finding that I wanted to highlight as well. And then they end with kind of these heuristics, these kind of rule of thumbs recommendations for LoRa. They recommend using LoRa for instruction fine-tuning and not continued pre-training. And as we saw in one scenario, instruction fine-tuning, LoRa performed better than full fine-tuning. If the GPU memory allows for it, they recommend targeting all transformer modules with a rank of 256. And then they recommend using an alpha value of 2R. And finally, they recommend sweeping over learning rates between 1e neg 5 and 5e neg 4, picking the highest value that enables stable training. So those are their LoRa recommendations. And one thing I'll highlight as a limitation or future work is that LoRa has inspired many variants and extensions. In this study, we chose to analyze the classic LoRa setup. While many of these proposed variations of LoRa seem promising, we leave a rigorous comparison of these techniques to future work. They also mention in the paper that they've only looked at 7 billion parameter models in this case, so obviously there's larger models that can be explored. And I'll recap the main takeaways again. LoRa underperforms full fine-tuning when the rank is low. And for continued pre-training, even when the rank is high, LoRa underperforms full fine-tuning. So this goes back to their recommendation of using LoRa for instruction fine-tuning. LoRa maintains source domain performance better than full fine-tuning. It mitigates forgetting more than dropout or weight decay, and it also learns more than dropout or weight decay in general. LoRa maintains diverse generations, maintains the generations of the base model, as we saw in that human eval generation 6 charts. Full fine-tuning learns perturbations with rank 10 to 100 times the LoRa rank. So that's a counterexample to the low rank hypothesis. And finally, LoRa is sensitive to hyperparameters. So really interesting paper, especially because it's LoRa and it's something us GPU poor folks can experiment with. I think it's really awesome to see this kind of work being highlighted. And that's the end of my presentation. I'll be doing more of these paper presentations this year, so keep an eye out for that. And thank you for watching.